Welcome everybody to our long-term cropping system studies known as Rotation ABC. My name is Ben Ellert and I'm a research scientist in biogeochemistry here with Agriculture and Agri-Food Canada. This is one of the longest running cropping system studies in the world. Established, the ground was first broken in 1910. And the sodbuster and the researcher arrived here at the same time. So we've got soil samples archived right back to 1910 here. The history of resource use and resource extraction in this part of the world extends back even further than that. You can go not far from here on the shore of the St. Mary's River, and the archaeologists have found bones of horses, not the modern European kind, but the prehistoric North American kind, and camels with butcher marks on them. And that happened about 11,000 years ago. 11,000 years, as far as soils go, is very young. So these are quite young soils in contrast to what you might find in New South Wales in Australia. So this has all been reworked and ground up and redeposited by glacial activity. These are lacustrine soils, so they're deposited by settling out of an ancient glacial lake. And since deglaciation, that 10,000, 12,000 years, there was ecological succession to the prairie grasslands, because that's the biome that we find ourselves in. We get about 400 millimeters of precipitation a year here. And thankfully, about 2/3 of that falls during the growing season from April through to the very end of July. Unfortunately, in this year, you've hit us at a time when we're, at this particular spot, we're about maybe 60%, maybe 55% of normal. So this is a pretty dry year, but not atypical. So at this site, don't be expecting cutting-edge agronomic research. This is a long-term agroecological study, and this particular plot labeled A, there was a systematic series of cropping systems. Today we still have rotations A, B, C, and rotation U, which is an irrigated cropping system study in a different part of our research center. Rotation A is continuous wheat. This plot has been cropped to wheat every year starting in 1911, and we've got records going back. The next three plots over this way comprise rotation C, and that is a summer fallow wheat rotation. Summer fallow, of course, that's not a current practice. The agronomists really frown on such things. I would argue that it's vitally critical for our understanding of the long-term, slow-changing processes that we're charged with monitoring. Long-term cropping system studies helps us address things like the sustainability of agriculture and processes that change slowly, or changes that are small and difficult to discern from background noise. And these studies like this are a listening place for us to monitor the long-term evolution of our systems and help us to assess our effects on them. So the wheat yields here range, 5-year running means, range from about 1 to 2 metric tons per hectare per year. In any given year, we get almost double for wheat that's on summer fallow than continuous wheat, because summer fallow benefits from some moisture, incredibly inefficient at storing moisture, but it does benefit from some moisture storage. And that is the furthest to the west section of each of these plots. The fertilizer treatments are labeled, and that is still check fertilizer. So there's never been any nutrient amendments applied intentionally on these plots. It's pretty tough in this wind. There's the yield chart going back to 1910. I can pass it around. Do you want to show it? And the scatter of the points should give you a little bit of a clue why it is so crucial to have these long-term studies because we've got lots of variability. The lines represent the 5-year running means, and there's a technology trend you can see on there. More recently, the yields have been going a little bit down because we're simply running out of nutrition, especially nitrogen. The unique thing about this study is it was native grassland, so we have a major land use change. When the native grassland was tilled and these plots were established, we changed the whole carbon and nitrogen cycling when we do that. And what we're doing is we're exporting wheat grain off the system, and that is sold traditionally on the domestic and international market. So that represents a nitrogen, phosphorus, and other nutrients that are exported. Starting in 1967, over 50 years ago, we added fertilizer treatments to these plots. So we've got a factorial combination. This center section here is phosphorus alone. The highest yielding section is the nitrogen and phosphorus treatment, and the farthest one is nitrogen alone. And of course, it's classic soil fertility where you need to supply all nutrients in a reasonable ratio. So the greatest yielding plots are the nitrogen and phosphorus. Currently, we've dropped that rate. It is about 10 kilograms of P per hectare per year when it's cropped. The fertilized plots, of course, or the fallow plots, of course, do not receive nitrogen. Let's see, the other thing that I wanted to point out on here is there's lots of interest in carbon cycling and the influence of human activity on the exchange of carbon between land and the atmosphere. And those are kind of messy measurements to make. But studies like this allow us to discern how carbon changes. And when you cultivate this land, we change it dramatically. And the main thing is we're exporting carbon off these systems, whereas that carbon would have been recycled locally in the native grassland system. So inherently, we lose about 25% of the original soil carbon that was here. These soils might contain on the order of 60 metric tons of organic carbon per hectare to a depth of about 60 centimeters. And we've lost about 25% of that. That loss largely happened within the first 3 decades of cultivation, and after that it's more or less stabilized. When we start adding nitrogen, that's when crop yields increase. And of course, we don't see summer fallow very much anymore. And when you switch to continuous wheat, as shown in that chart, it doesn't do a lot better than the wheat on fallow. But when you start to add nitrogen to that system, it pulls way ahead. Those yields are the unfertilized yields. And when we increase our yields, we increase the carbon return to the system, and we can measure those carbon inputs. On studies like this, because we have the archived soil samples, we can do analyses that the people that established these plots, they couldn't have envisioned. Analyses like detailed isotopic analysis. Isotopes, they're subtly different forms of atoms, and we're mainly looking at carbon and nitrogen atoms. So for this study, we can look at the changes in the natural abundance of carbon-13, and we've also done work on changes in the natural abundance of radiocarbon on these. And to the extent you can call it a natural change, worldwide, there's a little bit of difference between the northern hemisphere and the southern hemisphere, but humanity has enriched the atmosphere with radiocarbon from atmospheric testing of nuclear weapons. And we can actually trace that pulse of carbon through these systems, and they allow us to test our understanding as embodied in nutrient cycling models. So those are some of the things that we use these long-term plots for. The other thing I would like to point out is yesterday I was surprised at the interest in changes in pH. There was a lot of concern amongst our Australian friends, changes in the pH. These are very young soils and they are calcareous. One of the things that we have to contend with And maybe I'll just have, in a minute, I'll have everybody walk along the plots. But you can see we've got our enemy, the ground squirrel, has been digging in our plots, which is not a good thing for the soil scientist trying to account for carbon and nitrogen. But there you can see the subsurface, and it's very rich in calcium carbonate. So our pH here, it ranges anywhere from around 8 in calcium chloride, maybe 7.8 in calcium chloride. And in our fertilized plots, we do see a drop in pH in the surface layer by not quite 1 pH unit in calcium chloride, but still it's not we don't see that as a real big problem here. So, and that's sort of a function of the relative recent and the richness of the soils that the glaciers left behind for us here.
I missed it. Did you remove the chaff and straw?
Yeah, in this study, the only thing that is harvested is the grain. So the straw is all returned. And there's been a tremendous evolution in farm practices. This isn't necessarily a museum piece. We do not adopt every brand new change. We're using current cultivars of hard red spring wheat, so definitely the genetics have changed. Our weed control practices have changed. We've adopted selective herbicides. We've gone to essentially a very low disturbance seeding system. We use a disc drill. In the early days, when it's very important when we're modeling this, we have to understand they were using a stationary threshing machine. And in the stationary threshing machine age, everything above cutter bar height was removed and exported from the system. Since the adoption of the combine harvester, only the grain has been harvested. And that's a very important point when you're trying to model carbon dynamics in systems like this. So if there are any questions or comments? Maybe with that, what we'll do is we'll just walk along the ends of the plots and have you take a little bit of a look here. Yeah, so this is the strip, and that's the other secret about long-term cropping system studies. Similar to the situation, I believe there's some in the state of Victoria, in Australia, and at Waite Agriculture Institute. A lot of these studies were established, just like the ones at Rothamsted, before the concepts of randomization and replication were really worked out. So these are non-replicated studies, and that does have limitations. Had they actually been long-term randomized and fully replicated, those studies get very complicated and very expensive, and they never persist because of changing research agendas. These, you can see, they're long strips, large plots, relatively inexpensive to maintain for the long haul, and that's why they've persisted to this day.
Is there any rotation at all?
Tell us how you monitor these in terms of sampling.
Sampling, we measure grain yields, usually with a plot combine, and periodically we collect detailed quantitative sampling to measure carbon and nitrogen stocks. Every once in a while we'll have targeted short-term projects superimposed on these. We've measured greenhouse gas fluxes, detailed information on nitrous oxide emission. Our soils are a sink for methane uptake, and CO2 emissions, whatever that means. So if we were to measure CO2 emissions from the summer fallow versus the cropped plot, which plot is going to have higher CO2 emissions? Which one? It's got to be the summer fallow?
Because the crops take in the CO2.
No. We're measuring soil respiration, so we're measuring the flux of CO2 at the soil surface. And when you do that, you've got higher CO2 emissions from the crop plot because you're measuring plant respiration and the decomposer, the heterotrophic part of the carbon cycle. That's what really makes it difficult to use, well, I guess this is my bias as the biogeochemistry guy, but to use flux methods to disentangle the carbon cycle. When you measure canopy level CO2 fluxes, they change. The sign changes from day to night, and you've got to encounter every hour to account for that exchange. And if you do that, you're quite right. The fluxes should be high under the fallow because we're measuring plant CO2 uptake with those canopy levels. But when you measure soil respiration with the flux chamber, the fluxes are always higher on a plot that's actively has plants that are metabolizing. And so this is the continuous wheat plot. This one looks a lot like continuous wheat, and historically it performs about the same. Looks a little bit worse than that, partly thanks to our friends the ground squirrel that are doing the number on it. And this is the wheat crop that was grown on summer fallow. So last year this plot looked like that one, where we use non-selective herbicides to eliminate vegetative growth. And that was one of the early things in the sort of the history of agricultural development. And one of the things that has changed during time is how we manage summer fallow and whether we even have it in our system or not. Of course, we're pushing to intensification and getting away from summer fallow. The greatest loss of carbon, that 25%, happens in the one that's under summer fallow. We've got irrigated cropping system. Carbon cycle is totally different. We've removed a natural constraint on that system, the availability of water. In this environment, 400 millimeters of precipitation over 1,000 millimeters of open pan evaporation. So a very high evaporation rate, which makes for an arid environment. When we start pumping irrigation water on there, our wheat yields go from 1 or 2 metric tons to 6 to 9 metric tons. And that's just, there's other things. The irrigated system, we do have local recycling of manure in that system, and essentially we've maintained or increased levels of carbon in that study. And our work on the isotope levels, the background isotope dynamics, help us better understand these kinds of dynamics much more than if we only had carbon and nitrogen analyses alone. The isotopes really give us the edge on that. But this shows you a crop on fallow plot. So its benefit. Summer fallow is an incredibly inefficient way at storing precipitation, but in very arid years and in some years, it does make quite a difference. The yield plot, the yield chart that I passed around, that was system-wide yield. So you have to calculate the yield of a fallow wheat system, you have to sum the yield on this plot that looks not so bad with that one that looks pretty bad with 0 from the fallow. And that's how you get your area-wide yield. And that's what you have to compare with the continuous wheat. When you grow wheat continuously with adequate nutrition, it will out-yield and accumulate more soil carbon than any of the others.
What year did they go to canopy fallow versus the canopy cultivation for summer fallow?
That was more of a gradual shift, but I would say it was since I got here. So it would be by about 1998, we were pretty much no-till. But whether it's tilled or whether it's chemical fallow is a very minor effect than whether there is fallow in the rotation or no fallow. So with that, I'm afraid I would like to usher everybody back to the bus